Welcome to episode 3 in the video series, Making Sense of the International Energy Conservation Code for Everyday Life. I'm Gil Rossmiller with Colorado Code Consulting, and I will be your host. Today's episode is about how residential mechanical systems save energy. The last few code additions have increased our energy efficiency by raising R values and lowering U factors, and one may wonder how that actually increases the energy efficiency and saves energy of a home. The truth is that raising R values and lowering U factors in itself actually doesn't save any energy, but it does increase the ability for the building's thermal envelope to keep heat in or heat out. The energy savings is due to the fact that the mechanical equipment that heats and cools our home can be smaller and run more efficiently. A critical piece of the energy efficiency of our home is how we design our heating, cooling, and ventilation system.
Heating and cooling design.
So what is a Manual J? An ACA Manual J, ACA Air Conditioning Contractors of America, their standards writing organization, is a standard that then calculates the heat gain and heat loss for residential buildings. Heat gain would be used for the air conditioning sizes, and of course heat loss then would be used for the heating equipment sizing. Without an accurate Manual J calculation, heating and cooling equipment in the past were typically twice the size that was needed. Just think for a moment about the amount of energy we could have been saving if we had been finding compliance with this requirement for the last 20 years. When the heat gain and loss loads are known, the designer is then able to pick the equipment that is sized appropriately for the loads. This is where the Manual S process begins. A Manual D then is the design of the ductwork to distribute the correct amount of heating and cooling, air in this case, to each room based on the calculations provided by our Manual J. I know that many folks look at a Manual J and all they see is a mass of numbers and have no idea how to make head nor tails out of it. Do not give up. We're good on this critical calculation. Let me give you some basics and kind of help translate that massive numbers into a recognizable heat gain and heat loss calculation. There are actually several ACA approved softwares out there. Two of the most common that we see are called RightSoft and Elite. Both of these softwares have project design data that give the information about the project. We're going to be talking about it's going to give the location of the house. It's going to have the building's orientation, the elevation, the latitude. Next, you need to look at our outdoor dry bulb temperatures, which are the outdoor temperatures established by local code or Table 1A of Manual J. Just know that Manual J version 2, the current version, was published in 2006. And the weather data may be slightly outdated. All ACA approved software will contain updated weather data. Verify that the daily temperature range will be, for this project, maybe it's listed as high, low. The last portion dealing with the indoor parameters are either labeled as heating and cooling or winter and summer. You're going to verify that if the indoor heating or winter temperature is 70 degrees, that's what we're designing to indoor, and that the indoor cooling dry bulb temperature is 75 degrees. Next, let's look at the design percentage for outdoor humidity. For heating or winter, we shouldn't do more than 30%. We don't want to have humidity or condensation in areas that we don't want. And for cooling, we should be right around 50%. Last but not least is the moisture difference, or what we call grains difference. The key here in Colorado is that number will always be a negative number. Okay? This depends on our latent capacity, our latent loads. We don't have any we don't have no latent loads here. So depending on the software's weather data, you might see a range of a -25 to about a -55. The idea here, as long as it's negative, you're good to go. The next review is the construction descriptions, or what we call the component descriptions. Wall assemblies, your thermal envelope, their R values, their U factors, the area, the square footage of those areas. There should be certain we've all the types of assemblies are in the house that we're going to be using. Below grade walls, above grade walls, slab on grade floors, floors over, cantilevers over ambient air, roof ceiling assemblies. All of these values should be very close and match the values that are listed on the plans and energy compliance documents. Remember, these are the values to use to determine the size of our equipment to install. So these are all very important parameters that we need to make sure are there. Now, how many people they have in this building? The number should reflect the number of bedrooms plus one. We're not designing for the party that they might have. What are the numbers for appliances or equipment? This is a number used for cooling loads, things like ovens and refrigerators, TVs, dryers. You're going to have a load in there for that, and they should. The last thing we're looking at is ductwork load. Is the ductwork loaded inside or outside the thermal envelope? We need to know that. If we're showing a 0, there are no duct loads, that means that all the ductwork is on the inside. Okay? If we see a load, they had better have ducts on the outside, ducts in the attic, for instance. If they're showing a load and the duct's on the outside, they need to start over again. All this gives us heating and cooling calculation numbers. They're what we use to determine the size of the equipment the house needs. So as long as we've got those design parameters right, the areas are correct, the thermal envelope values are correct, we can depend that the load is correct. Manual S is the sizing of the equipment itself. What do you need to know about sizing? Well, you're going to need to know a few things about the equipment being proposed. Of course, you need to know what the output of the equipment is, but it goes a little beyond that. You're going to need to know what the efficiency of the equipment is. So for instance, this is going to affect the output of the piece of equipment. So we're going to have the input ratings and we'll have output. Remember that Manual J is what they list as the elevation of the project. So in Colorado, we're kind of high, meaning elevation-wise, yes? Mechanical equipment works better at sea level than it does at 10,000 feet. Absolutely. The equipment for gas-fired appliances, they will have a deration based on every 1,000 feet above sea level. Now this will vary amongst manufacturers, 2 to 4%, somewhere in there. This is why we need to have the manufacturer's performance data provided to us. Is it 2% per 1,000? Is it 4% per 1,000? Because we want to make certain that the output rating of the appliance works whether it's at 5,000 feet or 10,000 feet above sea level. That's a critical piece. Make sure that they've not only rated for efficiency, but also for altitude. Manual D, then, is the design of our ductwork. We're going to look at things like our external static pressure available, then pressure losses, and then finally our available static pressure. This group of numbers should be equal in a balanced type equation. If you add up our pressure losses with the available static pressure, you should equal the external static pressure if everything's added up right. We need to look then at our friction rate. That's probably the biggest deal. We need to make sure that they did all of their, grills and filters and what's gotten in the way. Once they do all their math and our total equivalent length, you'll have a friction rate. The friction rate must be between a 0.06 and a 0.18. If it's not, the system won't work. Then we should have a duct layout. We should a duct layout to see for everybody to review, to build, and inspect to. We should have the size of all the ductwork, all the fittings, the locations of the registers, and the CFM that we would expect at that location.
Common mechanical systems.
Okay, so let's talk about the types of mechanical systems commonly used in a residential project. Most places in the United States, we have a forced air type system. It's commonly used. What's a forced air system? Forced air system will use a source of heat or cool. So we got a heat exchanger or we got a coil. The conditioned air is then dispersed throughout the house by design ductwork through vents or registers. Furnace, right, is one type of equipment used for that heating system. Air is brought into the furnace by the return air plenum. Air is then forced up through the heat exchanger. Then air is heated by burning fuel source, right, propane, natural gas, or oil at the heat exchanger. Air is then forced through the ductwork, distributed to the rooms. Central air conditioning then is using a refrigerant. We're drawing heat out of the house and rejecting it to the outdoors. This is accomplished with our outdoor compressor condenser coil and the evaporator coil that's inside the furnace itself. The air then is forced through the cold evaporator that's inside the furnace, then right into the ductwork. Generally, most times our AC system is referred to in tons. Okay? Well, what's a ton? Well, it takes 12,000 BTUs in 1 hour to melt a ton of ice. That's where the ton comes from. So a ton equals 12,000 BTU. The higher tonnage result from higher energy usage. This is part of the required equipment sizing process, the whole manual S piece. So we don't have a 5-ton air conditioner when we only need a 2-ton. So an air source heat pump is a system that can actually transfer heat from the outside to inside the house. This happens when the refrigerant is circulated between the two coils, one included indoors and the second outdoors. So it looks just like a regular AC, except it has the ability to reverse the refrigerant flow. The indoor coils release the heat as the refrigeration condenses back into the liquid form. This process can be reversed for the cooling. This type of system can be used as ducted system or ductless. So you've heard of mini splits, yes? Basically, that's an air source heat pump. We can use this in colder climates and may have to have some backup heat. Supplementary electric resistance heat for backup. If it's utilized, you need to have controls based on section R403.1.2 that basically controls it. So we're not running backup heat when we don't need it, because it's very expensive and it's a waste. That you don't want the supplemental heat and the heat pump operating at the same time. These systems can use ductwork to get the conditioned air to where it's designed to. What are some of the requirements for the ductwork according to section 403.3.1? If located outside the building's thermal envelope, they're required to be insulated with various R values. Makes sense? Depending on the size of the duct and its use. We also are requiring that the ducts be sealed, along with air handlers, filter boxes, per section R403.3.2. Building cavities are not permitted to be used for ducts or plenums in any way, shape, or form. Let's look at a system that doesn't use ducts to heat an area, like radiant heating. We have two typical methods for this. Electric radiant panels that can be used. The second is hydronic, so hot water. That is directly circulated through the panels at various locations, floors or walls. Electric radiant systems have got electric cables built into panels. You can build it into the floor, you can build it into the wall. Hydronic radiant systems pumped heated water from a boiler through the tubing on the floors or walls. If these systems are installed in a slab, you need to have at least a minimum R5 underneath the entire slab, based on footnote D of table R402.1.2. The key there is with any radiant system, we want to direct where the heat goes. If we don't have insulation on that slab on grade, for instance, where's the heat want to go? Well, it's going to want to heat the dirt because it wants to go to the cold. You want the heat to go up, so that's why you have to insulate on the opposite side of where you want the heat to be on any type of radiant system.
Service water heating.
So what is service water heating? These are systems associated with heating the water for use in the home, so domestic hot water. What is the equipment used for this? Many types of equipment. Is the one that is very familiar with this is our conventional water heater or storage tank type water heater, which we commonly use. We could use electricity, we use natural gas, we could use propane for the process. The water's then stored in the tank for use. There are also things we call tankless water heaters that are becoming very popular these days. These heat water as they run through the heat exchanger, so there is no tank. Once it runs through the heat exchanger, they don't store any heat, it just heats the water instantaneous. So it's kind of like an instant water heater. Natural draft water heater is it's a tank type water heater. It uses a draft hood and relies on gravity for the flue gases to go up and out of the house. Power vented type water heater uses a fan on top. So you've seen those power vented ones. They got a plastic vent, not a P vent. On top that helps push the gas out of the house using that PVC piping typically. Direct vent water heater is piped to draw combustion air from the exterior and exhaust gases through a separate vent. So it's a lot like a direct vent fireplace. If you install a circulation type system or a demand recirculation type system, we have a couple of different sections, 403.511 and 403.5.2, that require controls for these types of systems. Any of those systems, it's going to require hot water piping to be insulated to a minimum R3.
Power vented water heater with recirculation pump in everyday life.
And here we have a power vented water heater. We can tell that by the telltale fan that sits on top. This helps vent the gases up through the second clue, which is a plastic vent for condensate. It's a condensating type appliance, so it'll have a condensate drain with the water vapor that builds up on that. And our topic for right now is this wonderful hot water circulation pump. And here we have a close-up of the pump itself. And this is connected to the hot water side of the water heater. It also has a very nice timer. This is a 24-hour timer. And generally you can set, well, if you wish, you can set it up as often as 15 minutes on and 15 minutes off. Typically, we're not going to see that. I personally have it set up for 15 minutes, running 15 minutes out of every hour. And then you set it to start in the morning whenever folks get up, and you turn it off in the evening whenever you're done using the hot water. Typically, when you're hitting the sack. So, in this particular setup, it's not a dedicated pipe that's what we call the hot water return line. It's not a separate pipe. This particular system actually uses the cold water side to circulate back through the system. And so what happens here is this is underneath the sink, and typically what you're trying to do is get it the furthest away. So the sink that's the furthest away from the water heater. So you're actually circulating that hot water throughout the house as much as you possibly can. And so as we saw when that timer tells the pump to turn on, this is a nice little valve gizmo that allows the water then to flow straight through to the cold water side. So we've got hot here on the left, cold on the right. And so it's got this nice little thermostatic valve business inside there so that once it reaches the temperature, it actually turns off. So that way you've got that hot water there when you need it, and you're not constantly heating up the cold water side. When you turn the cold water on this particular sink, if you happen to do it right after the pump happens to turn off, the cold side might be a little warm for just a second or two. But the key here is now that we don't have to let the hot water side run until the water gets hot. Like I said, I had mine set up for 15 minutes out of every hour. You might find that you want it more often than that, or don't need it that often. But it certainly saves water. It's a nice water saving piece. And this is what they call a cold water. It uses the cold water return.
Ventilation.
Build tight, ventilate right. This is a phrase we have all become quite familiar with. It is a perfect example of how the I-code family works together for safety, health, and welfare of the occupants. The building type piece in the IECC is contained within the building thermal envelope requirements. The whole house mechanical ventilation system requirement is in the IRC. The Energy Code also has a requirement for the efficiency of the fans used in the whole house mechanical ventilation system. Well, what are the options for a whole house mechanical ventilation? Oh, I'm certainly glad you asked. The code allows for 3 different ventilation strategies. The first being exhaust only. This could be a dedicated bathroom or laundry room exhaust fan. The second is supply only. This is where ductwork brings in outside air through ductwork into a furnace's return air plenum. The third is a balanced system, or as the code states, or a combination of supply and exhaust systems. This is where you would have fans and ductwork that bring in outside air and an exhaust system to the outdoors. A truly balanced system would have the same CFM for supply and exhaust air, like an HRV or an ERV.
Heat recovery ventilation, HRV, in everyday life.
So today here, let's take a look at HRVs and ERVs. This happens to be an HRV. So we have HRVs, heat recovery ventilator, and ERVs, energy recovery ventilator. They essentially work the same way. They've got 4 ducts that come into it, and I'll show you what they do here in a second. The difference is the HRV is just the heat. So the air that's going out has a tendency, and through the heat exchanger, the core, will condition the air that's coming in. Many of these are 60–70% efficient, so it's really a good thing to ventilate the house with. ERVs, an energy recovery ventilator, has a latent component. In other words, that the air that's going out has a tendency to dry the air that's coming in. So instead of having to dehumidify that air again, it's actually drying it out slightly. So let's take a look at how these ducts work. We've got 4 ducts that come into this system. We have the air from the inside of the building. So this is sucking air from inside of the building. We have a duct then that is air that's now coming back into the building that's filtered from the outside. We have the outside air duct. So this is the duct that's bringing air into the HRV. And then the exhaust duct. So this is the duct that's actually taking the air to the outside. And we've got condensate drains for the little pans that are on the inside. So we'll take a look at that here in a second. So what I've done here is I've just removed the cover to the HRV. That large square white looking thing here in the middle with the sticker on it is actually the core. On the top on either side are the filters. We're going to pull all those out here in a moment. You'll be able to see what that looks like. But first, let's kind of look and see what the air is actually doing here. So we've got air that's being exhausted. So this is the air that's coming from the house, getting exhausted out of the house, comes through the filter, through the core, then it is exhausted outside the building. Okay, so that's the air that we're pulling through. Now the core, which is now going to temper the air that's coming in. So this air now is exhausted to the outside. Then we have the outside air coming in. So as the air is going out, the air is coming in. It's all simultaneously. It's now coming through the filter, goes through the core, and then the fan takes it, and then our filtered outside air is then brought back into the house. And so let's take a look and see what's happening here. We're going to look at, so these are the filters. There's one on either side. They simply just pull out. These are the filters that need to be cleaned very frequently. I'm finding that I need to do mine at least once a month, and when there's more stuff in the air, I have to do it even more often than that, every couple of weeks. They get pretty dirty. especially the one on the other side, the one that's filtering that outside air that's coming in. Very simple to do. They're washable. You just put them in a sink with a little soap and water and let them, dry for a few hours and slip them back in. I've removed the filters and I'm now starting to pull the core/heat exchanger out of the box itself. Very clever device. You wonder how in the world we've got two different air streams going in two different directions so they don't see each other. We're going to take a look at each side of these and see that we've got kind of straw-like pieces that go in one direction and in the other direction they don't mix. Very clever. So here's the inside of the box with the cores, all the filters removed, and kind of a straight shot in. We've got lines here. You've got the red stuff, and that's the airflow from the inside of the house back through the fan there, and then it's getting vented back to the outside. And then we have that blue line of the outside air, then comes down through the core, sucked through the core, then air, it's conditioned, and then back into essentially the return air duct. Pretty simple stuff. You see the trays down there at the bottom. Don't panic, I'll get to the core. And the next shot we'll see is up above. Here I've just taken the camera, put it to the inside of the HRV, and just looking up, we see the ducts coming in for the inside air and the duct coming in for the outside air. So the core itself, this is the one view for it, and it's like we've got this series of tiny little straws that go through it. It is just like a piece of cardboard. If you've ever taken a piece of cardboard apart and you see the little straw-like or the little veins that go through it, it's exactly what this is. It's difficult to see through them. If you were to take this and shine it up to a light, you'd be able to see the light through these. Here I've turned the core simply 90 degrees. So this is looking from the other direction. It looks completely different, does it not? We don't see the ends of these little straws. What we see are the openings that are, quote, between the straws. The solid parts you see here are the actual straws. Those are the openings that we saw on the last slide. So we can see that the air never sees each other. It doesn't see each other. It just transfers our heat through the membrane or through these, it's basically plastic is what this is made of. And that's what transfers the heat, the air, through the membranes. Now here it's the same view that we were just looking at, but I've got a light on the back side of it, and you're able to see through that. So the same thing, if you were able to turn this 90 degrees, it just was difficult to get a picture with the light and the straws. It was tough to see, but you can see that we've got this nice piece where the air just flows through, heat gets transferred, and it works wonderfully. It's amazing, cool stuff. So there was the operation of an HRV. Hopefully that takes a little bit of the mystery out of it and how that heat exchanger and that core actually works.
I'd like to thank you today for joining us for episode 3 and hope you found it educational. Follow us for future episodes in the video series Making Sense of the International Energy Conservation Code for Everyday Life, and subscribe to our YouTube channel, Building Code Sense. Follow us on our Facebook page at Colorado Code Consulting, LLC, and at our website, www.coloradocode.net. And last but not least, the funding for this video was provided by Xcel Energy.